going to talk about numerical models of convection, and I think especially about the Taylor-Hartman theorem.
Extremely brief.
Extremely brief.
Okay, actually this talk was motivated by a discussion that we were having on the first day of the meeting about the solar torsional oscillations and whether its gradients are significant or not. So I'll talk a little bit about observations from both GONG and the MDI instrument on board SOHO, and later on I'll talk a little bit of theory which we developed to explain why the low latitude branch of the torsional oscillation precedes the sunspot cycle or the appearance of sunspots. So this is the regular solar differential rotation profile. So these are the color coded contours from the GONG data, and this is for the radial gradients. I'm sure you cannot see this. This is the radial gradient of omega, and this is the latitudinal gradient of omega. So and the units here are in nanohertz per solar radii. So you can see that the latitudinal gradients, it varies from say minus 200 to 50, and whereas the radial gradients are much more stronger. And for modelers like us, it is to some extent important to understand what are the differences in the SOHO and the GONG data, and which is the data that should be used, and what are the characteristics what are the characteristic differences between the two data that can affect the dynamo model.
So that's why you don't see here Tachocline.
Yes, because this hasn't used a Tachocline model.
It's a model, it's not observations.
No. The model that has been used for inversion is not a Tachocline model.
What do you mean not Tachocline model? One of the inversions.
Yes.
You get Tachocline from the data.
Yes.
Right?
Yes, but I think
But
there are
it's
two
of
different.
differential rotation by itself, not gradients.
No, but but to have the Tachocline, as in, well, I think as far as I know, I mean there are two different models which are used to invert these data. In one of the models, you have a sharp Tachocline over there, and one of the models you don't have.
One of the inversions.
Yeah.
You derive the differential rotation inside the sun, irrespective of models, right?
Yes,
That's what happens inside the sun. And we know if it was differential rotation function of radius, it has a Tachocline. It has a very sharp gradient at the best convection zone.
Yeah, but this paper, I mean, I can show you. I mean, they say that it's if you use a different model, you do get a sharp thing. I mean, probably it's a difference between the two models. But for the GONG and the SOHO, the same model has been used. So
Sorry, this is observations or modeling?
This is observations,
okay.
But there is helioseismic inversion in that. And to do helioseismic inversion, you need a solar model to start with.
Okay. And
Oh, you need only model for sound speed profile,
Yes.
but not for rotation.
Yes, that's right. I mean, I'm not talking about overshoot, I'm talking about the Tachocline. Because I think I can show you the paper actually.
Well, if you make a plot of rotation, the function of radius, if you just plot a rotation, angular velocity, the function of radius, then what we have here is Tachocline, point 7. Here the surface 1, and the rotation rate it looks like right?
Yes.
You go back.
Yes.
So this is called Tachocline.
Yeah.
So when you put a gradient, you see a very sharp feature at this convection zone, and we don't see this.
Does anybody else know this paper in more detail?
I think first I don't know, it was published or?
Yes.
I don't think it, but something.
But I mean, Sasha, on the other hand, we can do inversions subject to certain constraints. So, for example, I remember that Douglas Goff had the constraint
No, I think it's here that
where the
if a tachocline model obtained by Antia et al. 98 is used to define the rotation rate in the tachocline region, the gradient can be calculated more precisely and the results obtained using MDI data are shown in figure 2. It is clear that the gradient is much larger and more localized in the tachocline region than is seen in figure 1. So if you look at this figure 2, so here you have a sharp tachocline. Yeah. It's not from model. I mean, this figure.
It says model, but it says inversions.
Yeah, this is mean radial gradient obtained from MDI data using the tachocline model of Antia et al. 98, shown at few selected latitudes.
Maybe you should also look at result by some other people, not only by Antia.
Yes. But no, when I was looking at, I was talking about differential rotation gradients. So, I mean, this was the paper I had seen. So,
I mean, maybe
the results from this.
Given what you say, Sasha, maybe you should get this picture on your laptop, and then you can show it maybe in 15 minutes or half an hour or something.
But I would like, this is my full illustration. I am not so serious on this.
Maybe
So
is it possible to say several words about this program and how this program is different from the other observational program? This is seismology data, yeah?
I don't know how it's different from, why it's different from other, but it's also what's suspicious here that, say, when we do inversions, we put also some error bars, right? And here I don't see any error estimates. Because on the measurements, we usually put error estimates. And here we don't know if these features are real or not, because here we don't show any error estimates.
I think there must be error bars in the paper. I mean, at least this figure. I mean, you mean there must be error bars here on this? But
Yes, yeah.
the inversion errors, you mean?
Yeah, because now we don't know if these features are real or not, right? And in inversion, it's very easy to get, something like this when we don't even feed the data. Because inversions is feeding data, right?
Yes, that's right. You're basically calculating residuals.
And data, particularly for rotation, they have some errors.
But I think there must be something about the errors in the paper. I think, okay, I mean, maybe I'll just continue. So, even if you use that particular model, if you say that you're using the same model to invert both GONG and MDI data, and I mean, the basic difference between the GONG and MDI data is that the MDI data has the surface gravity modes in it up to L less than equal to 300. L is the order as in the YLM theta phi, and in the GONG data you have no F modes and you have P modes which are limited to L less than equal to 150, and in MDI you have P modes which are less than equal to 200, and with this difference, if you invert the data, we get certain differences in the outer shear layer between the MDI data and the GONG data. In the MDI data, the radial gradient in the near the surface looks much more sharper than in the GONG data. But if you look at the latitudinal gradients, they are more or less, I mean, they agree better than the radial gradients at least. And I mean, if you note the, this is the regular differential rotation, so this is 200 nanohertz per solar radian, this is of the order of 600 nanohertz per solar radian.
So sorry, so you're saying the near surface shear layer
yes.
is stronger, in which case again?
In the MDI case. I mean, at least in the high latitude.
Yes.
But then these people, they have done a calculation to find out why that is so. And it is not because of the F modes which are present in the MDI, not in the GONG, but because of the high frequency P modes in the MDI data, and I think it is
Yes.
well known that the MDI high frequency modes in the MDI data have some problem, or
No, it's no. First of all, you know that all the variations at high latitudes are fictitious
yes,
because data are not inversion is not reliable there.
yes,
And normally, when, I don't know what my anti did, but normally when people do inversions, they don't use high frequencies, even they include
yeah. I
the
mean,
tables.
in this case, the frequency
Because
for
it's,
MDI has been limited to say below 3 millihertz, and for GOM it's 3.5 millihertz.
So why is it
Because to eliminate the high, I mean not in this figure, but in the later figures where they find that the SOHO data and the MDI data agree when you eliminate the high frequency modes. So in the MDI data.
So what is the principal difference between two programs?
You mean
GONC and MDI?
Yeah, one thing is that the amount of data they have is different. The GONG doesn't have F modes, the surface gravity modes in it, which are actually very much concentrated near the surface gravity modes, whereas MDI has the F modes. So you might believe that, okay, if it has modes which are concentrated near the surface, maybe the MDI will give you better information about the outer, the rotation rate in the outer layers of the sun. But we don't know. I mean, these two data agree only when you eliminate the P modes. I mean, if you limit the P modes to 150 for both of these, then they tend to agree. And F modes don't seem to affect the inversion very much. Inversion for rotation.
I mean, can you maybe explain this business with these F modes again? I mean, there used to be the saying that the F modes are being are just surface modes, and one can use them to rescale the radius, I thought, or something like this.
That is what it is used for.
And so how come then there's such a significance in those? And also, why are they not present actually in the GONG data? Is it simply because of normalization issues?
No, I think GONG doesn't observe F modes. I think probably he can tell you better.
No, the problem is here that what you use, that what 115, that was GONG some years ago. Now they have GONG Plus, the upgraded instrument.
Yes.
That now they can see up to 300.
Yeah, but that
Same-
data
same
hasn't
MDI,
been
now
used
it's
for
same.
this study. So
I don't know what Andy did because he's always very selective, that so it might be very, very critical to what he writes. Because he's always very selective. And also, what the difference, the main difference between GONG and MDI, that the F mode is very weak at low L. That's the reason why they don't see. But now the upgraded instrument, they see F
and
mode.
they see the F
But
modes.
it doesn't contribute much to these inversions because it only very near
Then
the
it will
surface.
be important to use that GONG data to do the inversions again. That is what
The way difference
trying
between
to say.
results, GONG and MDI, they use different fitting for frequencies, different models for fitting. So the GONG, they look only at modes they are usually resolved because the modes, because of rotation, the frequencies are split. There's rotation
Yes,
splitting.
yes.
But splitting, because now it slowly, splitting is very small.
Yeah.
And sometimes, in many cases, it's smaller than the line width.
Line width of
Yeah,
the-
so the modes are not resolved. So they overlap. So then you need to
Then
take
it is not
into
possible to.
account when you measure the frequencies. And GONG doesn't do this. They don't take into account the overlap. They use a very, very old teaching code. So there's a
resolution.
difference. And MDI takes into account, but then it depends on how you model this overlap. So there's called leakage matrix in measurements.
No, but then I mean, what this paper claims is that, I mean, they have done is they have eliminated the F modes. I'm not talking about this figure. In the other figures I'm going to show in the torsional oscillation figures, they have tried to eliminate the F modes from the SOHO data and done a similar inversion, like in the GONG data. And they say that the inversion is more or less the same. The results are more or less the same between GONG and MDI. And the F modes don't affect the inversion.
It's also all done, including gradients in 1998
Yes,
paper by
yes.
Paul. So that was
Yeah, I think, yeah.
And even
comparison and explanation why they're different, all been done, including error estimates. I don't know why it's 10 years ago they not comparing
no, that may be because to study, now we have 12 years of torsional oscillation data. We didn't have that in the beginning when, when there was this paper by Kosovic and Skoun and where I tried to explain the solar torsional. That was preliminary data. So now
no, I'm talking about rotation in general, not
okay.
torsional oscillations.
This paper is basically focused on calculating gradients of solar differential rotation during solar cycle 23. So,
and did you compare resolutions of these two instruments? Which better?
Now they're the same.
Not the same.
Actually,
They suffered from steam clouds.
because it's
Because
telescope.
NDI is above clouds. But NDI, the difference here that NDI, they have only, with high resolution, they have only 2 months a year of data. And the GONG actually has better resolution now. Continuously, because they have continuous data. For the whole year.
Yeah, the
And
sun
they're only 2
never
months a
sets
year.
on the GOM network.
So that one,
There are 6 stations and each is separated by 4 hours. So they can observe the sun continuously. But then MDI also does so.
so the data are not uniform, so they're graded from time 2002 recently.
But maybe what we should look at is then the main outcome of this. So what do we, the features and how do they compare?
Yeah, these are the radial gradients of on the left side. The radial gradients at different depths. So this
Yes.
is at 0.98
Uh-huh.
and this is at 0.95, 0.9 and 0.80.
Uh-huh.
So the MDI and the GONG, they agree. Okay, one thing that I came to know from this paper was that there are differences in the regular rotation profile between the GONG and the MDI. But when you look at torsional oscillations, the results are more or less the same, except at the radial gradients near the surface, that is 0.98. So here there are some differences between, if you can see the contours here, between the GONG and the MDI. But whereas if you look at the latitudinal gradients, they agree very well. So the differences, one more thing is that these gradients are actually derived by subtracting the rotation profiles at 2 different times. So you just take an average rotation profile over one cycle, and then you subtract that profile from each epoch. So in that subtraction, the difference that existed in the regular differential rotation data between SOHO and GONG has disappeared in the torsional oscillation data. And just to look at the basic features here, the both in the radial gradient as well as in latitudinal gradient, they seem to encompass the entire convection zone. And in some latitudes, they would appear to propagate towards the surface, whereas in some latitudes, they appear to propagate towards the...
It is just simulation.
No, this is from data.
Why you have data for 2010?
It's a good question, yes.
Oh, no, actually what is done here is what dynamo theorists want to look at as a cycle. So what they have done is they have repeated this thing. It's one cycle, but they have just repeated it.
Excuse me, you told about observations.
Yeah.
You cannot
This is observations. Only thing is that the same structure has been repeated twice, so that you can see this. So that the brain registers the regular pattern.
But you don't know.
Well, we don't know, but this is a visualization thing.
So I need 2010 on the side.
And I should not put, 2010. You should repeat year also.
No,
Dates.
so what we see here is, but wait.
I think this is.
No, wait. This,
I think that it's just to say that there is a repetitive behavior,
yes.
but not that this is the data from
No, we agree
2010.
with you. Just, you cannot, if you repeat, the data, then you repeat also times, right?
Of course. You see, everything is, Sasha, I mean, Jan Steenflo has done this already back then in the late 80s. So that he calls this mode cleaning in time. So he has calculated the temporal modes, omega, and so a Fourier transform in time and then back again. And of course, then you can apply this to any time. It's just a periodic 22-year signal, 11 years.
It's periodic. Question is how it's periodic.
Yeah, but I mean, you can reduce the noise, of course, by this modal cleaning.
But really, magnitude.
If you don't want this, you can get.
I would request you to look at this figure only from a visualization point of view and not.
Okay, it's not.
I mean, not that there is really some data in 2010 or this is what the sun is going to do in 2010. No, that is not what the paper claims.
Of course not.
I mean, this is just for visualization purposes, especially for the dynamo theorists would like to see the solar that pattern in the repetitive pattern. So it is just to motivate that this doesn't have any other connotation. So that is what I would request you to.
Because we don't believe this dynamo is just periodic behavior.
Yeah, but I mean that's only since now, of course. If you look since 1960, between 1960 and 2000, of course, the sun has been superbly regular. It's only now that it all of a sudden deviates from this.
No, so here, another thing that I would like to point out is that the gradients here, you can look at the color bar. It is of the same units. This is again in meters per second of the velocity. I have another figure where we can compare the magnitude of the gradients. So I think this is a figure from another paper by Vorontsov et al. In Science. But here also they have kind of repeated this pattern here, and they have measured the. I don't remember whether this is from India or COM, but they had measured this in India. So here they have given the torsional oscillation pattern, the amplitude of the torsional oscillation pattern in the convection zone, and this is the phase, and this is the plot at the surface. So you can see that there is a high latitude branch which is propagating poleward, and there is a low latitude branch which is propagating equatorward. And here they have actually plotted not the surface velocity but the delta omega, or the angular velocity, which is in nanohertz. So if that is done, then the high latitude branch appears to be much stronger than the low latitude branch. And near the surface, the amplitude of these oscillations in terms of the velocity is something like 5 meters per second. So which is like 1% of the actual rotation.
So how does this then compare to the previous? Is that comparable or what?
Oh yes.
Yeah. Okay.
That is comparable. But here again.
What is the rotation rate of the sun?
Huh?
What is the rotation rate of the sun?
The rotation rate, and at the surface it is something like 1.4 kilometers per second. On the surface, the equator.
You mean in nanohertz, yeah? Or what do you mean?
How can make it 5%?
Kilometer per second.
That's what I said.
How can make 1% when it's much better?
It's something like 1,000 something meters per second. That's what I
So kilometers per
calculated.
second.
Yeah. 1 point something kilometers. Yeah, I mean it's less than 1% of not much less, maybe 0.0,
If
maybe
you take
0.05.
difference in
not
velocity. So 20% for rotation of equator rotation, maybe it will be 1% of 20%.
Of differential rotation?
Yes, maybe it's.
No, I'm not talking about a differential rotation. I'm talking about
but just
actual
a minute,
rotation.
it's simple to calculate. We've got 2 kilometers. It's rotation of equator. So it means that the ratio 5 meters divided by 2 kilometers, what's the ratio? Or something large. It's very small, much more smaller than 1%. So maybe if you take 20% difference between pole and equator and calculate velocity, it will be similar to this 1%. 5 times less, please. 0.2, I think, approximately.
In nanohertz is something like 400 nanohertz, 460,
Yes.
and it is 4 nanohertz here, so it's 1%.
Yeah, in that sense it is.
It's 1 nanohertz, isn't it? I think it
I
corresponds
mean,
to 1
yeah,
nanohertz.
that's right. So if you look at this at
It's
4
4
nanohertz
nanohertz.
by 400, then it is something like 1%. So I have actually said 1% of omega, not 1.
4 nanohertz, and differential rotation per, say, depth of convective zone, right? So it's 6 nanohertz per solar radius, say. So if we compare
Actually, it's not
with
6,
the
it's more than
400
that. It's something like
nanohertz
20 or
or
so.
200 nanohertz
So
per
if you look
radius,
at this,
typical differential rotation,
so
much
this
more.
is something like 10 or so. If you look at this, the gradients, this is the latitudinal gradient and this is the radial gradient. And superimposed on this is the sunspot patterns here. So this is something like 10 nanohertz per solar radial. And that you have to
10
compare it
nanohertz.
with the 200
Versus 400
nanohertz.
nanohertz or 200 nanohertz.
So then it
typical.
is something like 10% or so, and not, it is not negligible.
I mean, isn't one of the...
Differential rotation, 400 nanohertz or 200 nanohertz per radius.
260 nanohertz rotation. But when in this previous work, what I'm talking again problem with high latitudes, where results are completely unreliable.
yeah.
It's just extrapolation. You cannot trust this.
No, but but in this diagram, even at low latitudes, we have something like say 10. I mean, I won't go up to 20, but say 10 nanohertz per solar radii. And then if you compare it with the not this one, say this one here, then this is say this is something like say 200 here, and this is say something like 400. So then also it is something like 10% of the regular gradient. So no, okay, so
yeah, so I think in the next picture, yes, this one here. I think the important thing is to understand first of all what's the width. What's the width of the signal? I mean, the width of the high speed.
This pattern actually has been is at 0.95 solar radii. So in this pattern, they say that the butterfly diagram actually overrides the positive. What do you say? The larger than average radial gradient of the sun. So you see the pattern lies over this red strip here, right? And whereas if you look at the latitudinal gradient, the butterfly diagram actually lies on the lower than average latitudinal gradient of the torsional oscillation. So this phase relationship should be produced by dynamo models.
I mean,
this is something to look for.
That sounded a bit complicated, but isn't it what you say that the signal in the torsional oscillations comes before?
Yes, that is
before that of the magnetic field.
This is the actual torsional oscillation signal in terms of delta V phi at the surface, and this appears before the appearance of the sunspots here. But here I have plotted the gradients.
Okay.
These are the gradients. So this is d omega by dr.
The radial, yes.
Omega by d theta.
I see.
What for depth?
This is at 0.95.
What depth? Just below the surface, right?
No, this is 0.95.
40 megameters, yes?
0.98
kind of a theory that believes that it's in
yes, in that sense.
no,
No, but then if you have a surface shear layer, then I think it is important whether you are calculating at 0.95 or 0.98. If you have the surface, if you have the surface shear layer in the dynamo model, I think no, because the surface shear layer probably will be at 0.96 or 0.97, isn't it? I mean,
yeah, but that is important. If dynamo works in tachyc line,
we don't know.
so it's important.
I mean,
what if it doesn't?
Huh?
What if it doesn't work in the tachyc line?
Yeah, but what you said, dynamo theory should explain this, but why?
But we have people in the audience who do that.
Explain this, right?
Yes, yes.
Yes,
but that doesn't mean that it's a dynamo theory which has the which has magnetic fields produced only at the taper plane. I mean, it can be any dynamo.
Dynamo theory, I think, in general, can reproduce many mimic of this phenomenon. Of course, the main problem how to reproduce the solar cycle. And after that, this question will be much more simple.
No, even if you, I mean, for example, now we have a lot of dynamo models, but I mean, not all of them can explain all the observational features. I mean, if you try to explain the regular features, you don't explain the irregular features. And if you try to explain the low latitude features, you don't explain the high latitude features. I mean, a single model, I don't know of a single model which can explain all the features of things.
Very brave to say.
Theories of torsion oscillations, current theories of torsion
There are, I mean, people have done some work. For example, I mean, Sprout has this thermal shadow idea where the, and then it was further developed by, I think, Matthias Rempel, and he has some work. And they claim that the low latitude branch is actually because of thermal effects. And there is thermal effects.
Thermal?
Yeah. And the high latitude branch is because of the Lorentz force.
It's a thermal shadow thing, right?
Yes, yes. That is the
Parker,
I think developed by Sprout. So, and then
Yeah.
But both their models not related to dynamo theory.
No, Matthias Rempel has a paper, I think, has a couple of papers, I think around 2007, 2005, 2007, where he has actually developed a model which is, I won't say it is fully dynamical in the sense of direct numerical simulations which Axel does, but it has the dynamo equations, as in the induction equation, and 3 equations for the 3 different components of velocities. So one equation is for V field, and there are 2 other equations for the meridional circulation. And in that model, I mean, he tries to explain that if you have only the Lorentz force in your model and not the entropy equation or the temperature equation, then it is difficult to reproduce the low latitude branch of the torsional oscillation. Or even if you do that, they all line up on cylinders. So that is what he has done. But
Has he took into account the stratification of density in this calculation?
yes, I think he has.
In real
Yes.
solar level?
I don't know whether he has taken it from a standard solar model or not, but I think he at least has some polytropic dependence of density.
May I ask you a question? Have you noticed this signal of about 1 or 2 years? There's vertical columns in both of these charts. In the upper here and then in Chakraborty.
Chakraborty Chaudhary.
Yeah, and to the left one in the upper panel you also
This
see.
is for this figure.
Yes, but you see there is a certain columnar structure in the particular high latitudes of a period about 1 year. Yes, you see
No,
something.
I don't. Actually, this is from I think Doppler measurements from MDI.
I think it's artifact of observation.
So, yeah,
Why-
I think
I mean, but they
Soho
look-
has some kind of a
It's-
1-year periodicity in its data.
It's not a real signal.
No.
Are you sure? But it looks, I mean, you see similar things in radial magnetograms. Do they actually agree in phase?
This is actually a torsional oscillation.
Yeah, sure. But you see these these things which are quite well explained, of course,
No,
not very.
if you're talking about
Yeah.
forward migrating
Yeah.
strips, then those are real.
Yes,
Huh?
right.
But these are these vertical. I mean, as he correctly pointed out, and these are this. You can see this vertical.
Oh, they're just completely
strips.
vertical, yeah?
There is no indication of any transport
Yes,
there.
I see.
And
Yeah.
Soho, I mean, as far as my knowledge goes, Soho has some 1-year periodicity in its data, which is definitely not of solar origin, but must have some.
Okay.
Soho also goes around with a period of 1 year.
yeah.
So
Actually,
then there is some problem.
Okay.
carefully looking at that, I see it's a bit more than 1 year. Sounds like 1.2, 1.3. I count four features for 5 years. I think some might be different.
Yeah, this is actually not the P mode or the F mode data. This is the surface Doppler velocity measurement. So this is a different form. Yeah,
It's a real signal or not?
the surface velocity measurement.
I don't know.
That MDI.
The observers should address this
I
question.
mean, not this is not nothing to do with inversion or anything. Well, I think it doesn't really go up to the poles.
I mean, 50, we begin to see it at 60 degrees, right?
These are
whatever the motion
This
of
data
this
doesn't work
mission.
with phones.
I don't know,
70
this
or
question
70
should be addressed to observers.
But we are all happy
To
to
people
I mean,
accept
these
that
are
you
not
are
who are in the
holes.
station, it's in the signal.
These are not 90 degrees, 90 degrees.
Earth's orbit is not exactly circular. It varies. So 1 year signal.
I think I'll have to check my paper one second, but I think it was something around, the data which was given to us was I think from 75 to 75.
You know,
I
never
think we
do
extrapolated.
problem.
I think we
So the
extrapolated.
correction is not quite
We did.
fine.
We,
You did.
yeah.
You know, correction of
Which data
material
use different types of data? Use full disk.
it's
No, actually we took this data from Todd
a
Hoxema.
bit longer than that.
Todd Hoxema?
That can be an artifact. Because
No, the torsion oscillation data.
what I suggest
The color
is to
plot.
wavelength the data and see what sort
The
of
color plot
changes.
data was given to
And
us
from
by
wavelength,
Todd
it's 1
Hoxema,
year or not.
and this is an observational plot. I mean, we basically did the theory and we compared it with this observation. We didn't process the observation. We took the observation or borrowed the observational data from Todd Hoxema.
You know, the whole synoptic map
Yes,
was given by Todd
Yes,
Hoxema
yes.
before.
yes.
So we should ask him about this, how this was measured.
Yeah. I mean, since we were doing theory, we didn't bother about those things.
What?
Actually. I mean, since we were building up a model, and it was a very regular model, and we didn't bother about.
What's the model?
I mean, these the periodicities. He was talking about.
Because this, when you're going to show this plot, right? It's you have time and latitude.
Like superposition of
So this somehow is average over rotation period.
and the signal is 1.5.
Okay, you are asking about. Okay, this was given to us for every Carrington rotation, but we averaged it over 20 Carrington rotations, and then we got a smooth.
Why 20?
That's why I got this periodicity.
Again. So that's explanation, not the precession of the mission.
Yeah.
What was the
Why
reason?
20?
Sorry.
Not 13 or 10?
I mean, after 20, averaging of 20, we probably got a profile where we could really identify these.
Butterfly.
These strips here. Otherwise, the data was very noisy, and we were not able to see that strips very clearly. But then if it's 20, it would probably be something like 2 years or more than...
Yes, exactly. The signal I see is a bit longer than 1 year.
Oh.
Could be 20 Carrington rotations, because 1 year is 13 Carrington rotations, almost exactly.
Because now here when you do when particular polar regions, when the Carrington maps, they're very distorted. Because Carrington rotation corresponds to rotation of the sun at 16 degree latitude, right?
I mean, this data was actually in the format of Carrington rotations. So for this Carrington rotation, for say first Carrington rotation, there was a map. For second, there was another map. So it was like that.
Yeah, but it's usually used for magnetic field because in polar region it's very distorted. Because rotation of the polar region is much lower than,
Yes,
and then you have kind of lag, right? So then you have inconsistency in these maps. So you cannot really look at the polar branch and doing it this way. Because you cannot just average over the same period of time because that rotates in different period, right?
But then it is okay for the equatorial branch, right? And that is what we wanted to look at. I mean, the low latitude branch. So, I mean, our theory focuses on the low latitude branch.
And yeah, it's not very good for this type of measurement. About leakage of, look like a lot of
Yes.
some leakage of magnetic field, there's a distortion of, so we must be very careful. But that's data from our observatory.
Axis is
So we look at velocities for torsion
we
oscillation.
have data up to 2010. I like it.
Mark Wilson.
Really know how to do
Yes,
it.
yes.
For 3 solar cycles, torsion oscillations, certainly proportion.
data.
Really, this left hand is pure observation?
This one? This
Left,
one?
yes.
Yeah, this is pure observation.
And you are trying
This
to
one is also observation.
yes, you are trying to relate the equatorial branch to solar dynamics.
Yes, yes.
But in the left hand, it seems to be that torsional oscillation starts
Oh,
early
okay.
than.
These are the gradients of torsional
But looking at down in the bottom,
here.
yeah, torsional oscillations start early than the strong magnetic.
Yes, that is what is the observation is about. That the torsional oscillation is actually starting before the sunspot cycle, and if the Lorentz force is responsible for these torsional oscillations, then this looks like an apparent violation of causality, right? I mean, you see the effect before there is the cause. So before the sunspots come on the surface, you have the torsional oscillations.
It will be naive. You've got waves, you've got production of waves, you've got specific
Yeah, that's
waves.
the reason.
You should calculate this phase shift, because it's not phase shift between.
Yeah, in fact, I mean, in our model we have used the Alfvén waves to propagate the torsional oscillation.
Alfvén waves is nothing with this phenomena, I think.
And what? You use
Yes.
Alfvén waves for analogy or what?
Huh?
You use Alfvén waves for analogy.
It's a phenomenological thing. Again, a phenomenological
Yeah.
thing. in the
But with the
model.
Steinbock waves, you can do the same thing,
No,
right?
the idea is, okay, I'll explain it to you as I go on. So, okay, so from this part, we can just say that in the time-dependent pattern, there is reasonably good agreement between the MDI and the GOM data at all depths, except at very near the surface. And the torsion oscillations penetrate most of the convection zone. And at 0.95 solar radii, the magnetic butterfly diagram coincides with larger than average radial gradient and also with smaller than average latitudinal gradient. So this is an important thing. And another thing from observation is that the equator propagating branch at low latitudes seems to have a phase lag of 2 to 3 years at the surface compared to the oscillations at, I mean, this will not be 0.7, but near the base of the convection zone.
You don't see torsion oscillations under the convection zone. Nobody sees this.
I mean,
Maybe that you
no,
discovered.
for, then, I mean, for example, you have this figure, say, okay, not at 0.7, but if you go at, say, 0.8.
Yeah, but no, it doesn't go to 0.7.
Well, I mean, they have calculated something here, I don't know, I mean, about the authenticity, correctness of that, because I have to do this analysis. I mean, I don't know about how correct this is, but, I mean, they have to
But
do
there's some
this.
later papers, you know, that trace of how you know all these.
Racial law, yes.
So you don't refer to these. Because she studied all this in detail. And, you know, torsion oscillations at all latitudes, they're not seen in tachocline.
Okay.
In tachocline, they see some, you know, variations, maybe speed at 1.3 years, but nobody's seen their oscillations in 11-year period.
Yeah, but I think Rachel, they found this oscillation of 1.3 years in the tachocline, but no other group could reproduce that. I mean, that is what I heard. I mean, is that a real oscillation or
No,
is
it's,
it
we
some
don't know,
other
you know,
kind of data?
it's very noisy because when you make notes like this, right, observations, you have also the block error bars.
Yeah, I mean, even
So
this
then-
paper,
then
for
it's a
example,
real note, right?
the data
Yeah.
appears very clean. So you would, looking at this, think, oh, this probably
It
comes
also
from a
knows
dynamo model.
if
or
I says,
something.
if I say
But
the
this is
same
really
way,
from observations.
you know, it's not, they're not observations, you know, it's again, it's the same data repeated, you know, that
Yeah.
occasionally
Yeah.
a very narrow strip,
Uh,
noisy strip on
I think this
on the
paper
left.
came out in 2000. I don't know actually which part, because they have, unlike the previous paper, they have given the actual time, so you know which part of the data has been repeated. Here, I mean, the time is, so I don't know which part has been repeated.
No, we know what the time because, you know, this graph was in
Probably this is the actual
1999,
part.
yeah,
This is the part
1999,
which has been repeated.
But all these, you know, plots, you know, that behind this, you know, black line,
Everything
they're
is
not
repeated.
observations. It's a peak in a model. Because observations are noisy on the left.
Yeah.
And you see no signal tachocline because, you know, what is on the right, the whole periodic part.
There is still some
It's
signal
not
in
data,
the
it is
tachocline, but then-
sine function, periodic sine function to this part. These own observations, this from
Yeah,
0 to...
they have used a 11-year, whatever, not
Well,
11 years, 5-year thing to repeat this. 5 or...
Okay, listen to me now. MDI started in 1996, right? This paper published in 2002. We have only 6 years, That's this narrow strip on the left. It's actual data. Everything beyond 6, it's like anti-edit, repeating periodically. But here they also, if you read the paper, they fit a sign function. So these data are not real. It's a fitting of sign function. That's why it extends to perfect
No, this is
line.
not real. This is not real.
I don't understand why.
But still, in this region, you do get, they have some signal in the tachograph.
Well, they also reverse sign.
And that's the reason when I repeated, they have this.
Sasha, how you can explain different amplitude of oscillations on the middle plot for different strips? Different.
No, in the middle is the same.
No, different.
No, maybe because of the color coding, you find that the amplitude is different.
I think blue is the same as CD. No, it's periodic. Just
You can see on the right strips.
well, something is color metric.
I mean, the color coded thing can always be
in the
missed.
paper it explains that they teach the sign function to this.
Yes, they have.
Because
Yes,
the real
they
data
have.
is only the first 6 years, and not realistic here. And if you look, the noise is very high, below point 8.5. So everything below 8.5 is noise. So torsion oscillations, they have not been seen in tachocline. That's my understanding of this. So that's data.
No, I'm not
Maybe
claiming
that's
that they have
discovery,
been
but
seen
I don't know.
no, I'm not claiming that they have been seen in the tachocline. I mean, that's the reason I said that there is.
It's a great discovery if the last point is correct.
Yeah, I mean, probably this should be 0.7, but probably it should be 0.75 or 0.8. What I mean is, from even at 0.8 solar right to the surface, you have the phase difference of 2 to 3 years. That is seen in all.
I found a few interesting pictures which cover a
That
period
is a
2010, 2015.
Well,
Where they come from?
several years ago.
In that paper, figure 11, figure 10.
But it's at 0.85 something, it's not 0.7.
Not even 0.8.
Rachel, how you know this paper?
I know her recent
Screen
work,
from
but not the one you are
April
talking about.
6,000. It's okay.
It was the paper analyzed all the whole 11 year, like every year we have update of the result before show was analyzed this concept and the data and that's all documented.
Now, may I ask you to show another picture just above of you? This one. But a positive thing is that here is the period starting at somewhere 96 and ending in 2015 or after. How should you explain this bit?
You should explain it.
Periodical continuation of the real.
It has nothing to do with observations.
Until now.
That is what I was telling you.
Time machine is just fantastic phenomenon.
It is like a periodic box.
And I mean this, I don't think, there is anything wrong in representing the data in this manner. I mean, only thing is that people should understand that, this is not real data, and this has only been given for visualization.
Well,
I mean, it's cleaning in time. That's what it is.
No, this I
It's
don't
model
think-
cleaning in time.
This
is a standard
this has been
technique.
cleaned in time, I think this has been repeated. Unlike the next one by Vorontsov et al., where they have cleaned in time. Here, I don't think the data has been cleaned or anything. I think it has been
No,
cleaned.
they were because they cover the period of data which is beyond the real observation.
I mean, you just shift it by, you just time shift.
No, I think this is because it looks completely periodic, it must be model cleaning in time. What is that?
But actually,
All of
if
that.
we start from 1950, this observation, and make continuation for 5, 6, 10 years, it will be very good. But we've got just less than one period.
Yeah, I know.
That's,
Sure, that's a problem.
It's just for, how to say, for demonstration.
Yeah, of course.
Some people know, say in 2020, will read this paper and will be thinking,
I think every people would should have that much of.
What's his name? Father of Ilka. He observed torsional oscillation. Dominin.
Ilka, yes.
You know, father of Ilka. He observed torsional oscillation in 14, I remember correctly, first time. In sunspot motion.
Is that what motion is?
Yes.
So he recognized it first, not Howard and Labon, before Howard and Labon, many years. I should check in my papers. I would like to say that this picture, at least surface picture, was represented not so bad in the middle of 80 and in 90 in some of papers of our group and of Schuster group. Maybe they were similar papers of Schuster. And at least phase shift between activity and torsional oscillation similar to observation. It was long observation, 20 years I think. Howard Labon paper.
82 you mean, right?
More, yeah. First was Schuster, after our paper with Sasha Ruzmakin, 1948, incorrect paper of Arkady Zakharovich Dolginov, and after that Rudiger.
Yeah.
And then our paper with Ziegler and
Well, it was also, I think,
Ishimura. Maybe, yes, I don't remember. It was many
they
years ago.
developed quite good theory.
Yes. So interesting to compare these theories, all theories.
Part of is that, you know, we don't, no, can you show again the plots where we have the previous one? Oh, we have more material, I'm sorry.
Which one? Did you want to-
Well, this one, if you look at, if you look say at 1996, right, you can see a strong torsion oscillations, but almost no magnetic field on the surface. So something here in the low.
But it's again,
By the way, this data has been
if
repeated.
sunspot is threshold phenomenon, you had some magnetic field, lower than, say, threshold, but magnetic field, not far from surface of solar surface exists, even if you have magnetic sunspots.
Yeah, no, but you know, if it's a Lorentz force, right, and somewhere below the surface, you drive into the storm, then because, you know, density decreases very rapidly, you know, the upper layer will just move, you know, this.
It's not so, it's a tricky business. You should put very carefully boundary conditions. Let us discuss it. It's not so simple because, in some sense, you sum of viscous stress and Lorentz stress equals 0. No, nearby surface. It's an answer.
Well, it's not, viscosity is 0, right?
Viscosity is 0 from from a sphere, but not in solar convective zone. So it's not okay. We'll discuss. This is the question.
Yeah, okay, so I mean, as far as, now you know that the torsional oscillation originates a little bit earlier, 2-3 years earlier than the advent of the first sunspots of a cycle. So now from the surface it appears that the effect is actually manifesting itself before the cause comes. So now if you believe that the Lorentz force is actually, the back reaction of the Lorentz force is behind the torsional oscillation, then how does the torsional oscillation reach the surface before the start of the magnetic activity? So to explain this, we start with a flux transport dynamo model, but with a slightly deeply penetrating meridional circulation. And let us solve for the Navier-Stokes equation for V phi only and not for the other components. And we allow Alfvén waves to carry torsional signal but no mass flux to the surface from the bottom of the convection zone by adding an extra advection term which is of the order of 3 meters per second, the equation for V phi. So if I can just draw the toroidal fields are forming here, and here you have the convective eddies. And in this intergranular lanes, you have your magnetic field lines like that, and so on and so forth here. So, and if there's a Lorentz back reaction acting at the foot of these, I mean not foot, I don't call it foot, but at the base of this, it may be possible by these. It may be possible for Alfvén waves traveling along these field lines to transport the signal to the surface of the solar surface. So basically we start with a dynamo model which was developed in our group and has been described in these two papers. And we add another equation which includes the Lorentz forcing. And this is the tachocline over here, and this is the deeply penetrating meridional circulation. So the deeply penetrating meridional flow allows formation of toroidal field at the a little bit below the tachocline, and then it penetrates into the stable layers, and it can be prevented from erupting to the surface. And while this is being stored in these deep layers, the torsional signal can be carried towards the surface by the Alfvén waves in the model. So I agree that this model is a very what to say, I mean ad hoc. I mean the effect of the Alfvén waves have been included in a very ad hoc manner in this model. But just to see what happens in such a case, so I mean I have just compared the observations with the theory here. So in our model we actually get a little bit more than 2-3 years, maybe 3-4
What
years
boundary
before.
condition can we use in this equation?
What?
Boundary condition.
Boundary conditions.
Yes.
Boundary conditions, V5 has been put to 0 everywhere in these boundaries. And I mean, we calculate from 0.5 solar radii to the surface. And
And what is called it in 5 solar radius?
oh, the Prandtl number is 1.
Turbulent Prandtl number. It's of course okay.
Yeah, the turbulent Prandtl
solar
number
radius.
is 1.
Corona, you got turbulent. 5 solar radius.
So,
5 solar radii?
what 5 solar radii?
Is that how?
My question is, where you put
0.5 solar radii?
0.5.
0.5. 0.5. And what's the boundary condition on the top of solar conductor?
It's V5 is equal to 0.
Against observation.
I mean, we have used both actually.
It's
V5 is
against
equal to 0 as well as
observation.
V5 is
V5 by GR.
DR equals
I mean, you know, stress-free. Why not stress-free? Stress-free would be the normal thing, right?
Stress-free because you have got Lorentz force.
Well, I'm not sure.
Yeah,
maybe.
but then the total stress.
Maybe,
course.
sorry,
Total
I think
stress.
we have used a stress-free, which
Yeah.
is V5 by DR
Okay.
equal to
Okay,
0.
so it's one of the variants.
Not V5, sorry. It's V5 has is 0 surface. So if we look at the, this is the plot, this is the radial direction, and this is the time. So this figure is at low latitudes. So the Lorentz stresses are still concentrated in the tachocline because this is a tachocline diagonal model. And the torsional oscillations are actually launched at the base, and they propagate upward due to the Alfvén waves, like that. And this at least agrees well with this work. Whereas in high latitudes, the physics is slightly different. In high latitudes, the Alfvén waves, the transport by the Alfvén waves, torsional oscillation transport by the Alfvén waves has to compete with the sinking meridional circulation, which carries the colloidal field downward. And the latitudinal shear here acts on the colloidal field to produce the toroidal component and thereby the Lorentz stress. And this meridional circulation then moves the region of the Lorentz stress downward. This is not the color-coded part, but I think this is not visible. There are contours here which actually go downward like this. These are the contours for the Lorentz force. And these are actually, the color-coded thing is actually the contours for the torsional oscillation, which still look like they are propagating towards the surface, whereas the Lorentz force center is actually propagating downward.
What is calculation propagation of Alfvén waves?
Huh?
Can you tell more about the Alfvén waves? What the frequencies, how they excite, how calculate propagation of Alfvén waves?
We have not
In what
included
sense
all
are
that
many
in the
equations?
model.
How many equations? You need two equations at least. You've got one equation. I don't understand again, actually.
No, I'm talking about Alfvén waves.
So what we have
No
done
other
is
frequency.
no, this is the Navier-Stokes equation for V5, right? And then in these advection terms here, advected by this VR and V theta. So in VR, apart from the meridional circulation velocity, there is another velocity which is a V Alfvén, and that has been taken to be of the order of 3 meters per second at the base of the convection.
This is what the physics, what the minimum is. It's not Alfvén wave. What is this? The Alfvén.
There is no Alfvén wave.
No, we know what meridional circulation is. It's a flow of material.
Yes,
Flow of material.
yes. This Alfvén wave transport is not flow of material, but it is only that the torsional signal is being transported to the surface.
What's the physics of this?
Yeah, that is what I explained here. I mean, there are these convective eddies here and the intergranular lanes. You expect to have magnetic fields. And it is through these magnetic fields that the Alfvén waves can, and if there are Alfvén waves here, and then these Alfvén waves can carry whatever information or whatever is happening here to the surface.
Alfvén waves don't transport magnetic field.
They don't transport magnetic field, but they are transporting the no, they are not transporting the magnetic field. They are transporting the V5.
They're not transporting V5.
Why not?
Well, you know what Alfvén wave is, right?
Yes. I mean, it's just transporting that signal from the one place to another place.
No.
That certainly it can be.
Do you know what Alfvén wave is?
Yes.
Huh?
Yes.
Can you explain us what Alfvén wave is?
Yeah, I mean, Alfvén waves, I mean, they travel along the magnetic field lines, and suppose, I mean, it's like you have a guitar and you just pluck the strings, and the kind of vibrations you get, and Alfvén waves are same kind of vibrations but on magnetic field lines.
Okay, so draw Alfvén wave.
Probably it would do something like
So we
that.
can see velocities, up and down, right? In
Yeah.
Alfvén waves.
Yeah.
So how do we transport? It's just
No, this is the amplitude of the oscillations. But the Alfvén, there can be a, there can be a direction of wave propagation, right? That is the velocity that we have introduced.
they don't transport, this is totally ad hoc and physical.
It may be ad hoc, but I don't see how it is unphysical.
Well, because an Alfvén wave, it has oscillations, up and down, right?
Yeah, but still, I mean, but still,
We need
I mean,
meridional
after
field
some time
in order
probably
to
it will
test
do like
torsional
that.
oscillation of this
Right.
sphere, right. From pole to pole. It's possible. It's another mode, totally. If you take toroidal fields which start from, say, one pole to another, in this situation you can get torsional oscillation. It's an interaction of this equation and equation, induction equation. It's so-called Markov waves of Braginsky. You can image one line which start from one pole, arrive to another, and after that you've got something similar to Alfvénic waves.
It's not pure.
Not this, of course. It's not.
Not this time.
It's a slightly different. I agree with you. It is another picture.
It's not included. I don't understand how you can improve.
But it is not the Alfvénic waves again. It is just Lorentz force from dynamo which drive this motion. It is, in some sense, it is a standard model. Question is, what actually happened on boundary layer, in boundary layers? How
I mean, any magnetic disturbance here will give rise to, will produce Alfvén waves, right?
No?
No, it's not, because you need to put another equations.
Well, we need to know to...
No, I'm not producing Alfvén waves. I'm not
If you just
producing.
shift, if you have just a stationary motion, you don't generate
But Alfvén waves need not be standing waves.
to generate a wave, right? Like full oscillations.
Yeah.
You know, tightening oscillation, you oscillate something, right?
Yes,
It moves
yes,
up and
yes.
down.
Yeah.
What is moving up and down here?
But that is
Or,
no.
you
But
know,
they are
you know,
like
back and forth.
no. But they are like standing waves. These are not standing waves. I mean, waves do carry energy, right? I mean, waves can carry energy and matter. But here, I mean, any magnetic field disturbance would produce alpha wave in a system. But I am not producing alpha waves in this model. I am just assuming the effect of alpha waves in the model. I think it is important to distinguish between the two scenarios. In a completely dynamical model, you would need to produce alpha waves then and there to transport the oscillations. But I am not producing alpha waves in my system. I am just assuming that there is an effect of alpha waves in this manner.
But you include in the transport, some additional velocity, and to play the deep alpha waves, and to include in the transport equation. And transport equation is the consideration of momentum, right?
Yes, but
So
still,
that's how we can
still it is not transporting the mass. It is only transporting the effect of the Lorentz force to the surface.
I mean,
It's
does
not transporting
anybody
mass
else have
because
some
I have no
opinion?
conservation of mass equation.
Does anybody else have some opinion on this issue? I mean, this is something that needs to be clarified, of course, needs to be done carefully. Not just.
It's not a very quick, of course. It's not a very quick.
Yeah.
It is, some senses, I find, maybe I'm not completely right, that the standard model of torsion oscillation was derived by Schuster first. We've got normal Lorentz force, phi component, and we've got equation for motion in phi direction. So it is simple equilibrium between viscous torque and Lorentz torque, nothing else. Next question, what actually happened on the boundary? And the difference, or believe that viscous stress equals 0 is one possibility, or total stress equals 0. Viscous plus Maxwell. It's another story. The result is different. It's not the same. But I'm pretty sure that we haven't any sign of Arvenic phase in this equation. Because for Arvenic phase we need additional equation, induction equation. And we should drop viscosity from this equation in order to get this oscillation. Because if you've got viscosity, quality of our oscillating system is very low, and we have a periodic signal in this situation. So I'm not sure that the interpretation is good. That's my opinion.
So I did not understand what is the other equation that you are suggesting? The VR and the V.
You know, for Arvenic phase, you need two equations.
No, to produce Arvenic waves.
In order to produce Arvenic waves, you need two equations.
Yes, that's right.
First one is say this, and second one for magnetic field.
Yes.
For BFI. BFI.
Yeah.
So what picture which you mentioned theoretically was studied by Braginsky in context of.
No, but
you start from this.
I hope, you know what equations, we are also solving the induction equation along with this.
You're right, but you solve induction equation in the dynamo approximation. So you've got in this equation very strong magnetic diffusivity. If you've got strong magnetic diffusivity, the oscillation doesn't exist. Because, if you've got a oscillating system and very strong losses, instead of oscillating mode, you will produce a periodic. You've got waves, but it's dynamo. Nothing else.
Yeah, that's right. It is not possible to produce alpha waves in a system where you have high diffusivity. So that's the reason we are not producing alpha waves in the system.
So, but it's not Arvenic phase. This field, BFI and polarity one, is not Arvenic.
No, they are not Arvenic.
But Arvenic waves means.
I mean, this is a misunderstanding. She is talking about something else. She is talking about an additional model, and which, of course, Sasha and you agree is an additional model ad hoc, on top of that.
But
for propagating the information from the bottom to the top. Isn't that what you mean?
Yeah.
So that's something which is not in this
there
equation.
has to be a different model to produce alpha waves, but we are not producing alpha waves in the system.
Yeah. And whether or not we want to advise this is another question.
Yeah,
Right. So maybe we should not, or we cannot address this here so quickly.
Well, but nevertheless, if you've got enough strong viscosity, Alvenic mode as oscillating mode doesn't exist.
Yeah, but I'm not sure that applies. I mean, for the same reason, P modes wouldn't exist. But
What mode?
P modes.
P mode. P mode. What can I say? If it's enough shorter than the size of your convective element, in this situation doesn't exist with turbulent viscosity.
Yeah.
But if it's so long, the scale of
and is it long, Piali? Is it actually long, or what, are you thinking of high or low, short wavelength?
Short wavelengths.
Short.
No. What is the question?
How short this wave number? Of
the Alvin wave. Is the Alvin wave not?
Number that is not a parameter in the model.
But it's short or what? It's not long.
That has
it's not
been
comparable to the depth
calculated
of
by
it.
assuming that the mean field is something around, say, 300 to 500 Gauss, and then whatever the rho is something around at the bottom of the convection zone is probably 0.2.
So you calculate on the speed?
Something. So you just say, what's it, 4 pi rho or 2 pi rho?
But the question was, what is the K, wave number?
That is not a parameter, so I mean.
The frequency of Alvenic waves is K multiplied by CA. CA
Doesn't really matter in this, as she's.
So that you can probably.
So maybe you're right that there's no any. It's impossible to interpret this phenomena by means of Alvenic waves. Yes. She used one equation, but speak about Alvenic waves, which determined by
She
that.
didn't claim that her model should
Interpretation
explain
maybe is
the
not good.
production of Alfvén
in
waves.
dynamo model, no
If there would
Alvenic
be
waves.
Alfvén
In
waves in the
dynamo
system,
model,
they
they
would
would
probably
just
propagate
dynamo
with
waves.
the
It's not Alvenic.
With the
not
speed
depending
line.
on the wave number. They would be propagating
With
with
the
the
particular
speed of the Alfvén.
Yes. No, they include. They can think that they include, but again, dynamo model and this equation together
Due to the turbulent
may
viscosity.
produce. But if
The
separate
is
is
small.
Then should be there, right?
If small, then
plus induction.
this equation.
But not automatically. If
I
you
understand. It's a very
quality
good point.
of your oscillation system enough high.
To be clarified.
Okay.
Look at linearization of dynamo theory, momentum equation to see what kind of distortion relation.
I mean, everything should be included. I mean, it should be a direct numerical simulation. But, I mean, we cannot. But a direct numerical simulation has to first produce the regular butterfly diagram, then we do other things. So until we have that, we have to work with tools like that. There is no that is what I'm trying to do.
Okay.
I mean, till we can do everything by direct numerical simulations, we really have to keep doing things which are ad hoc, but
My problem here is that when you have this ad hoc model, and then you can match observations, and then you start believing that your model is correct.
That is something which we should abstain from doing, because this is an explanation for this, but there can be alternative explanations as well. I mean, it is important to keep our minds open. That's what.
If you physics correctly, that if you talk about Alfvén waves, then you should write equation for Alfvén waves.
Yes, that's right. But as Nathan was saying, that we cannot have. I mean, in a kinematic dynamo model with turbulent diffusivities, we cannot have another module which is producing Alfvén waves and feeding into the system, because the Alfvén waves would die out because of the turbulent viscosity. That's what you were saying, right?
But if you've got very short waves, say either corona or maybe infrasorbent to say, because the scale, less than scale of energy contained eddies, in this case, viscosity may be much less. And in this situation, this wave scale can exist. Yes, so small scale possible, large scale not. It is interesting.
Well, small scales are done very quickly because of,
But in small scale, your viscosity is very small. Because you've got scale dependent viscosity.
So in that case, there must be some kind of a scale selection for the
Maybe.
wave number of the Alvin wave, which is able to carry the. But Alvin waves do really carry magnetic disturbances at least, and that is the main thing that I am trying to invoke in the model. I mean, it is nothing
It's
else.
also questionable.
So yes, I mean, it can be questionable in the sense that this is not dynamic. I mean, how can you? I mean, the fact that this is completely ad hoc can be questioned in various manners. But if you just for some time, if you think that okay, let there be Alvin waves which are carrying the torsion signal from the base of the convection zone to the surface in whatever way, I don't know, then can this be explained?
Well, I know that they can, people explain the whole, solar cycle by Alvin waves, that Alvin himself,
Influence of large planets.
Alvin himself developed a theory of solar cycle based on Alvin waves.
No, that's natural for life.
Okay, thanks, Kelly.
Okay, no, thank you. Thank you for listening.
I will try to be short, but I'm not
Yeah,
sure
well, we
now.
don't have anything special during the afternoon.
Okay, so I don't need to be short. Okay. So
You have to be short before people start.
okay, I see. What died?
Yeah, before people see lunch.
Okay, lunch is. I will speak about differential rotation, more precisely about influence of heat flux, turbulent heat flux. And this work was done in collaboration with my, 21 or 22 years collaborator, Igor Gachevsky. So he sits now in this audience. I want to speak about convection, it's a nice phenomenon. If someone very interested, we can discuss. I will speak just about differential rotation. Differential rotation, we know fortunately from Galilean seismology, and what we can say that at least nearby surface is a rotation frequency increase in depth. After that, decrease more and more stronger, but for enough high latitudes, it decrease. After that, it's more explosive and decrease very strong. We've got several challenges in this. First of all, what's the reason in general? Second one, we believe that turbulence stops more or less in this position. Why we've got something similar to differential rotation after 0.7? Not good. So, of course, I'm not so, how to say, ambitious to say that I know all answers, but I've got at least some ideas. Let us discuss. First of all, about my first claim that is standard today for many people model of Günther Rüdiger and Leonid Chekinov, at least not totally correct. What would I like to say?
Totally complete.
Complete. No, correct, complete, what you like. I'm not enough polite person in English, unfortunately. If we start from average equation of motion, it is much simple to equation of PLE, it's not even more simple because we have a magnetic field. We've got two Reynolds stresses, R phi direction and theta phi direction, and we can split these stresses in two parts. One of them is traditional, it's turbulent viscosity, and two contributions. It is more or less proportional somehow to rotation. This guy proportional to differential rotation, and this to rotation. We calculate first, several years ago, Leonia and Günther calculated more than 10 years ago when we first discussed this stuff, second term. First of all, before we start, okay, no, okay, let me come in again.
What is this tau?
Tau, it is Reynolds stress. Tau is Reynolds stress. Theta R phi component, R phi. So we differentiate this component and find contribution to phi direction. This is theta phi component. We derive this term in respect to theta and find again phi component. Combination of these two effects gives us differential rotation. Of course, we've got influence of Coriolis force on medial circulation. This is velocity UR, U theta describe large-scale medial circulation. But we can drop it because at least it's not far from surface, and we will discuss more or less phenomena not far from surface. I explain why. This term is small. You can compare. No, of course, it is.
Depends on medial flow, right?
Yes, but if you take standard estimation, right, it could be possible, but if you take standard value, say 10 meters per second, which not is according to if you know enough information, I can agree with you because we're observer. But what I know it is 10 meters per second. 10 meters per second.
No, it is 20 somewhere.
20, no? Okay.
Okay, 2 times.
2 times. Okay, but in some sense it doesn't matter. It's just because I pretend to demonstrate solution of this simple equation. Almost analytical in some sense, as I would like to stress. If you so rich and you've got huge computer and enough computer time, you can solve all problems more correctly. Of course, I have no doubt. I would like to demonstrate some problems and some solution of these problems.
So what is this tau?
Tau is just nothing but rho u r u phi minus this tau r phi rho 0. Rho 0 u theta u phi tau r theta phi.
And one is proportional to the heat flux.
No, it is not. No, it is tau. It is tau in general.
Yeah.
We split in two contributions. This so-called lambda effect of longitudinal contribution. These contributions are new. First, we discuss features of this contribution. Lambda effect, it is a result of Coriolis force, contribution of Coriolis force to this term, which is proportional to square of gradient rho divided by rho. It is lambda effect. It is effect of anisotropy. In some sense, it is Masutinski effect, which recalculate in quasi-isotropic turbulence, which anisotropy just result of gradient of density. And no direct contribution of heat flux.
What turbulence model we use for this?
Huh? What model? For
turbulence is averages, you need a turbulence model, right?
Yes, turbulence model I will write you immediately. Just a moment.
I mean, in the equations of Günther's, one just assumes an UR squared phi, UR squared averaged minus U phi squared averaged. And that determines
they make
directly
many
lambda.
calculations. The model what they use.
You can of course calculate that then.
It is something in this spirit. It's okay, UA UJ equal. Let me include space. Right. Are you agree? Okay. Fraction operator, Pij, delta Ij minus Kij divided by K square, minus lambda squared divided by 4, plus lambda I Kj plus minus lambda J, I don't remember by the way, lambda Jki, and this, all this, and maybe I, and all this stuff multiplied by u square 0, and this of course some spectra. Roughly speaking, I minus 5. So that is more.
The second term should be tensor.
Delta J.
Yeah.
Right. It is more.
What the physical minimum is?
Meaning signal, this model means that
enough general
divergence
model.
of UI
There's
to
one
J
preferential.
equals 0. It's so-called most isotropic model which coincide with anelastic approximation.
This is the reason for differential rotation.
This term, this term is the reason of differential rotation.
How can you explain this physically now?
Physically, no, it is what actually happened. Element. It is, I should explain not my theory, you know. It is a little bit. Okay, but as I understand, again, as I understand, you elements go up and arrive to situation, then density inertia. And because the density inertia begin to spread out. And in this moment he lost, in this situation he lost moment, and how fast it changed gives you different, some flux of moment. Of course, our effect I explain much more better. I don't remember all details, but anyway, this gradient, this anisotropy gives you possibility to transport moment. And what's the main feature? Equator dissipation faster. But what's interesting is that as a result, give me demonstration simple. Rotation increase to the surface, not opposite. Okay, but we've got much more serious troubles with all models. Let me demonstrate. This is how Coriolis parameter omega tau. Tau is just, it's not tau, excuse me, tau F0, L divided by V. How it's changed in convective zone, according to model of Spruit, say. And what we see, after less than 10% of 20% of depth of convective zone, we've got something larger than 1. Omega is solar rotation multiplied by turnover time of turbulent theory. Yes, Michelin theory. It is just a fluid model. And it's changed. You can see that it's 20. It's huge. But even not far from surface. Just less than, again, third of convective zone. This parameter larger than 1. And we, fortunately, with Igor, studied what actually happened with viscosity for fast rotation, turbulent viscosity. And what we find that for motion, for eddies which rotate around global rotation, in horizontal plane, viscosity may be negative. We don't put this result. It's viscosity as a function of this Coriolis parameter.
Well, this is natural because fast rotation causes turbulence tends to be two-dimensional.
And then the situation may be unstable.
It's the same omega, right? Small.
It's the same omega. Simple, different papers, different graphs. So.
Yeah.
And it's very bad news. So it means that all our theory, which is based on the picture of turbulent viscosity, this one, for example. Huh? Equation 4, suppose we've got global rotation. We've got some direction, and we now split U motion in rotation in this direction, in eddy, it's rotating in this direction, and vertical motion. So in other words, we can rewrite U velocity, total velocity, U z is function of say coordinate and time multiplied by unit vector plus some say some vector potential. No, it is similar to representation in the toroidal and poloidal field, but for motion. And if we take curl twice, we will find this guy.
So what is W here?
Where W it is? W, it is curl of U in that direction. So if you've got rotation,
Now consider cylindrical components, right?
yeah, in this partial case cylindrical, but of course it's possible to rewrite to spherical, and never mind. But what's important, that for enough fast rotation, this positive may be negative. So, next.
Which
So,
is unphysical.
Unphysical, because we study 3D turbulence. If we jump to 2D turbulence, we will restore, of course. So, my idea, what I would like to stress, that for fast rotation, impossible to use model of isotopic turbulence, which people use in order to describe turbulent viscosity. But this nice model is totally wrong.
So, Nathan, your argument is that the turbulent viscosity must not be negative. This is the anchor point of your argument. Is it true?
What I would like to say, all mean field theory based of 2D facts. We need both positive turbulent viscosity and turbulent diffusivity. If not, you should add high derivative, which restore in very small scale stability of your equations. If not, you haven't any normal theory. It's just.
This was in our original theory for differential rotation that you have negative turbulent viscosity.
In original theory, we haven't negative. But in original theory, unfortunately, we never thought about situation with fast rotation and viscosity. We just put it ad hoc without serious analysis. Maybe it's first attempt to analyze what actually happened to fast rotation.
You know, was a book, some many years ago, over the author, big star, some famous meteorologist, who explained, because also in planets, we have differential rotation, right? Quicker is faster. It's explained by negative viscosity.
Yes, it's another story. Negative viscosity in 2-tier turbulence. But I know these people, and they use special, very strange features. They should, took this moment as a result of friction, surface friction. What kind of surface friction we have in surface situation? Yeah,
but
it's a boundary condition, but the physics, it's again
physics, in some sense it's physics. Okay, what I would like to say. You can speak whatever you like. If you use mean field theory, your transport coefficient should be or positive, or you should derive equation of fourth order at least. So it means that this frequent approximation, gradient approximation for Reynolds stress and for electromotive force, if you've got problem with diffusivity, is not enough. Nothing else.
But this is, it's not so
But
clear.
maybe he will.
I want to say on this, you allow that an alpha effect makes the system unstable, but you don't want to allow that a negative
For very
beta
simple
makes the
reason.
system unstable. For what reason?
Matthias, that's trivial. Matthias,
It's not
we
trivial.
discussed it many times.
Yeah, but I never
I
understood the
Matthias,
point.
it's misleading. Because
Gamma equal K alpha minus K square beta. It is normal situation. If now K enough short, automatically we stop instability. If we're so unlucky that beta is negative, we cannot stop instability. So
Of
our
course it can.
how?
Because beta is quenched.
But even the quench should change sign.
Yeah, why not?
Quenched by what?
Okay,
By the
okay.
mean field.
If you know how to do it.
yeah, Nathan, it doesn't.
Okay, friends.
Okay.
But my claim, in some sense, trivial. If omega tau larger than 1, we haven't good theory. We should think very carefully what to do in this situation.
When it's on the right side.
On the right side, I will discuss.
But by the way, is there also, under the same conditions, does the passive scalar diffusivity also become?
I'm not sure that
No.
it's much more complicated business. It's because in any case it's vector. It's another story.
Yeah.
There is a difference between two.
Yeah, it's not the same. Okay, let us discuss now what actually we've got. This red line, this is the field of my interest today, was right side. Because just in this place I'm ready to discuss theory. in more depth we should think more. And what we see, let us start from Tichettinov individual result. Interesting feature of this stresses, this is positive. So it means that J explained just this part. And this drastic down, it's positive, very difficult to explain. And in this sense, in this sense, we have a theory on the basis of lambda effect. What we do with Igor Rogachevsky several years ago, we calculate contribution. Roughly speaking, Tichettinov and Röger's theory is not convective theory. They put as a starting point Navier-Stokes equation, formally wrote in this equation buoyancy force, but never studied real influence of flux of entropy. For these people, buoyancy force just steering force and nothing else. So it is just a dynamic theory. Because yes, but just velocities. But we have got instead of velocity this guy. It's plausible that sometimes velocity produced not only by
once again, we go to same often like here in our right, so you ad hoc something that is not.
It's not at home. It's not at home. I can write in this, for small rotation, again, I can write by equation that give me possibility to calculate this torque as the base of this flux, but plus differential rotation, for example, or magnetic field. So it's not the same, these guys. Plausible, then again, it's another story, nearby Tachot line, that you haven't serious flux of entropy because it's close to zero, but nevertheless, because you've got differential rotation, you've got stress, you've got zero negative. But next step, okay? I will finalize this. I've got enough slides. All answers, no, not all, many answers at least.
But FR is just the radial flux, you mean, or what?
Huh?
FR is just...
FR is it means, FR means
heat flux.
Yeah.
Heat flux is just UR multiplied by S. S or theta, what you like. In this context it's theta, of course, it's potential damage. It is flux of entropy of potential damage. Thermal flux. Equation very similar. What's the difference? Difference is coefficients. And first of all, this sign. This sign is negative, and in his friends, this sign is positive. So, and another story, this effect, because we've got this parameter 1 and this coefficient 2, the ratio of two effects, at least 7 multiplied by L rho divided by L naught squared. So if you theoretician, you will see. Huh? L rho, L naught what? That is L naught is relation scale of L rho minus 1 just gradient rho divided by rho. Oh, okay, no, theoreticians, as myself Weber, believe this is large parameter. But unfortunately, no, because it depends on not rho, but depends on P. In
Newton theory,
in Newton theory, it's maybe smaller than, I would like to say, it is even, this parameter even larger than 1. Because normally it is LP.
I don't know, but
Huh?
it's sort of 1, or the unity.
In our definition, right? No, 5 maybe even.
Okay,
let me demonstrate the result of a gain of model of spruit, how it depends on depth.
Yeah, I believe this, yeah.
So it's really, it's as close to 1, you're right. But it's less than 1. Less than 1, because von Witten's it's not beautiful, it's more sophisticated, not Witten, not von Witten's. Because in more modern theory, L naught it is scale of pressure, not of density. 1.5 if you remember. No, okay, never mind. But what I would like to stress that is coefficient less than 1. So difference, if you take interesting for us part, this coefficient means that our effect, roughly speaking, 2 times larger than of Rüdiger.
I mean, can you maybe go back again? I mean, this Günther expresses these things not in terms. I mean, the previous one or some other one.
Günther
cosine.
expressed the result.
I mean, of course, he has an expansion in terms of cosine, sine theta, right? So I'm talking about. I'm talking about the first equation. Is it u r phi?
This first equation.
Yes.
This lambda effect.
Yeah, the whole thing. The whole thing in square brackets, certainly also.
But the brackets is function of omega tau. If we work not far from surface,
yeah, but the question is what is the sign?
Equals 0 to 0.
So the question, so the question is what is the sign? The sign is
positive.
Of Günther's.
Yes.
Yes, and that means.
But it means that you know by surface.
But he does.
Angular velocity increase.
I think we need to compare it not to the sign, but relative to 1 or something like this. Is it bigger or smaller than 1? Because he expresses this in terms of sine. He has an expansion in sines, not in cosines.
But you can, it is the same.
Yeah, right.
One
that
minus
means you have
sinus
to compare
squared cosine. But I speak not about latitude dependence. It is more or less okay. Pay attention. It is minus. And this is
opposite differential rotation.
yeah, you have to
polar. When theta is large, this contribution is negative, cosine dependent. So equator rotate more faster.
In your theory, it's opposite.
In our theory, no. This is
Because
because
same
it's minus and plus. So the same sign in this.
No, the first term is responsible for.
Yeah, first term is not proportional. No, the first term is not proportional to theta dependence. Because if we speak about omega, omega is just u phi divided by r sinus theta, right? So this sinus theta disappears both in this place and from this place. And so what we've got pure effect is this just first term, or this first term, for radial dependence, for radial. So for radial dependence, the effect is opposite, at least nearby surface. And for theta dependence, they walk to the same direction. Increases.
The same sign.
Capital what? T, it is still a temperature, absolute temperature. Because if we speak about buoyancy force, it is just potential temperature divided by absolute temperature, multiplied by G. No, if you don't like this, you can think that is entropy flux and reduce this.
These are just the non-diffusive contributions, right?
Yes, it's a post non-diffusive.
Yeah.
Post non-diffusive. Okay, let me continue. And so what I would like to say, that nearby surface, our term is negative. He is larger than the Günther, and he explains behavior of radial profile which we observe. And in more depth level, it's impossible to explain, I think, what we observe in helioseismology, because our models of viscosity is not enough good.
You can explain this jump.
No. Question to
Just
question to what is the name? Kingsbury. It is true, but we got from him data and calculated. I don't know. He had some jumps. Okay, if you're interested, I will explain. I can read it.
Computers were invented, right, or something like that.
I'm ready to explain what's the origin of Newton. If you like, I will do it immediately.
So that's PhD, right?
Yes. But I would like to explain not this jump. I would like to explain what the reason of new contribution is proportional to entropy flux. If it's interesting, I'm ready to.
Can you show again equation? The previous slide, yeah.
Yes. Okay. This?
Yeah, I would say this. So to explain, so what you said is to explain now that the gradient, the it's a radial gradient, right? Because your term is bigger than their term.
Okay. No, of course. Let me jump a little bit before.
But then we have problem with differential rotation, because then we will not match a longitudinal differential rotation.
Okay, let us start. We have got this equation, right? This basic equation.
Yeah.
Now we can take, if you believe that Newton somehow
numerical simulations that explain differential rotation, longitudinal differential rotation.
Define profile with similar to this one.
Yeah, and also with radius, except the surface layer. They explain differential rotation in the bulk of the convection zone, except Safek line and subsurface shear layer. Okay, numerical simulations.
No, I think if his simulation, more or less, not so bad, I think he take into account fast rotation. If it's taken into account fast rotation.
It's automatically.
Yes. And again, it's not so automatically, because his relay is very far from reality. And we don't know. He put some parameters which give him possibility to build something similar to observation. But I'm not sure that it's real. It is model. Okay. So it is model which describe more or less, say, global high dynamic. It should be, of course, because what can I say? Mean field equation.
No, but the reason I'm asking, because they also talk about thermal beam and the role of thermal beam.
So this stuff.
Theory.
Yes. No, thermal beam.
If you compare it with.
We don't compare, because again, we cannot do it, because impossible to compare our primitive turbulent viscosity with 3D full dynamic calculation. It's impossible thing. It is problem. We should build, how to say, reasonable theory of turbulent viscosity. Just after that, we will be ready to compare. Because you mentioned that his theory similar to observation, just in the depth, not on the surface, not on the half-life.
Well, because simulation is not able to measure
to reproduce. Okay. We speak at least a very thin layer, unfortunately, because turbulent viscosity is very restricted. Again, we're based on the normal mixing length theory. Mixing length theory produces turbulent viscosity, which plausible, but problem is that omega tau much larger than 1. So we should rediscuss it, and after that we will be ready. Now we're just we are ready to compare with your observation.
Well, another test of your theory is if you look at the very subsurface layer, there is a supradiabatic layer, where with your theta, it's quite different, from the other, from deeper layers. So you should see a jump in your stress.
But it's automatically if you've got jump of.
You can see a very strong change in rotation rate.
I've got observation. I've got observation.
Yes, yeah.
So it is strong.
From F mode,
it's strong.
No,
not strong. No, maybe.
No, it's not. It's like this layer. This continues. There's no jump, up and
No, I'm not sure that you think we've got. What I would like to say, gradient of temperature should be jump. But flux, I'm not sure, because flux is conservation. We've got no gradient of potential temperature, we've got flux.
Yes.
And flux is conservation. Why it should jump?
Because it's flux, it's heat flux is transported by radiation in this layer.
Right. So. Okay, it's decreased. So I think in our situation it should be. So is it unstable until?
It's unstable.
Unstable. So it should be something, and very close to this situation should be zero. So
I'm just saying that.
Okay. Interesting to check. I agree. Let us discuss.
Now this has nothing to do with the counter wind flux, right? That's a different thing.
What? Counter wind?
Yeah. What is the relevance?
Okay. What is counter wind flux?
I mean, it's not relevant to this, is it?
It's relevant. It's relevant. It's another, how to say, manifestation of the same phenomenon. Counter wind flux means if you've got profile of velocity, and you have got a flux of entropy. In this situation, you've got additional flux just opposite to velocity.
This is the flux. I mean, you showed earlier omega cross r. Doesn't this point in the phi direction?
Yes. But phi direction is precisely a velocity which is associated with rotation. In this sense, it's similar. I don't say that it's the same, but it's similar.
Yeah, and the divergence, if you have an axisymmetric model, the divergence vanishes.
Of course.
Yes.
But not divergence of stresses. It's not the same.
But contra-wind flux also can follow if you derive equation for the balance equation for the heat flux. You always have the term like F nabla U large. This is just contra-wind flux.
And if we speak in this language,
Yeah.
we've got term 2 omega cross F, or maybe opposite,
Yes.
in equation for flux. And we resolve this equation in respect to F, we find our contribution. In this sense, it's exact result, what I say.
So, yeah, this result is independent on closure in some sense. The
Mhm.
presence of the contra-wind flux
Contra-wind flux
is
or
independent of
contra-rotative
any
flux.
closure.
I see.
It's
Yeah,
a
yeah.
fundamental thing.
Yes.
Contra-rotative.
And yeah, but I think that's what is related to what I said in Slovakia, that this actually goes back to ideas of Goff in Douglas Goff.
Right. But unfortunately, I don't know this paper. You promised me to send reference, but you not sent it yet.
I mean, the reference is in our paper.
Okay,
we will discuss this.
we will. Okay, but you
And
mentioned it difficult to find.
Yeah, this is true.
Maybe you can ask
Maybe you
to
can
help
this paper.
to help us to find this information.
But contra-wind flux is known long ago, since 1972.
Maybe even before it.
Since Derdorf, classical Derdorf paper.
In meteorology. But again, it's meteorology.
Yeah, it's known, but it doesn't matter, it's the same equation.
Okay.
It's classical.
And then the sign of the right.
It's a very interesting plot. You can see this. Yeah, we can see this square, black square. It corresponds to the peak in differential rotation. I think it's accidental or.
I don't know. It's interesting question. I think in this moment our contribution will be the same as Axel, Günther, and the result step by step maybe will be even stronger. But again, all this picture, special picture of Günther, I'm not sure this correct because he used this model. This model is it possible to use for this deep layers because again omega previous parameters so strong.
And also it's natural that if you have two different vectors, one is the homogeneity of density, another is rotation. So you have to construct even this tensor with the two different directions.
No, I agree with you. It's just, it's curious.
Yes, it's curious.
Yeah,
I agree. I pay attention too. I don't know. It is a question. So nature say that okay, it is similar to our results, and after that to Günther more. So
my other question is that what can I make? Now we expect some results from other stars. We have some recognition.
Good question. Of course.
Other stars.
Okay. Again. Okay. It is. What can I say? If we've got very heavy stars, so we've got convective core. So we've got radiation core, and as a result, flux is opposite. So I think we should get in opposite to this behavior.
Okay, so we'll prediction.
Interesting.
For what? Rapid rotation?
Rotation of star spores, and maybe some.
Okay, very interesting. We'll be very happy to think about it. Yeah, because it's funny. What we don't know of paper, it's our of Goff. It's our fault, of course. Our fault. Yes. Yes.
How the stars predict for the opposite.
Okay. Thank you.
Okay, maybe it's now time to pause for the lunch and the presentation by Petri. Maybe we postpone it to the session for next week or after lunch. What do you think?
Next week.
Next week? Because there will be a session on convection.
No, I can prepare much better for next week.
I think this discussion for preparation.
It's new results during this program, of course.
Thank you. For me, it was very wonderful question. What I would like to stress. We never got this so far. One wonderful question. In Slovakia, we hadn't any questions at all. Practically. So,
actually, I would like to.
Interesting thing. We've got two contributions. Okay, but you know,
battery is doing almost like, not almost, but similar simulations as Bruna and battery. And he was going to talk about them.
Yeah, but I mean, to test this sort of thing, we should use something much more simple, I think.
I think my calculation is
In terms
very
of
simple.
simulation.
Your calculation is much more serious and it's impossible even to compare.
No, the problem, Natan, is when I give lecture to students about differential rotation, that's to explain this, in simple terms, how to explain this, that's what I ask you. But, if you write, that's not for students,
For students,
You have to explain physics, why it rotates faster, where
It's very simple, because then I arrive to the next layer, the velocity will be less, and push him, and stop. No, he go up, say. No, not negative viscosity. No. You speak about negative viscosity?
No, I mean...
Two questions. About our effect, it's very simple. The element arrives to a high level with low velocity, linear velocity. As a result, he, stop rotation. Break rotation. If you got some element which have less velocity, break.
No, I'm not talking about this radial, but longitudinal.
Longitudinal is a little bit more complicated stuff. Yes, we should think how in simple. But I think it's the same.
By the way, this shell was explained by, before it was discovered by Peter Foucault, just simply as conservation of angular momentum.
But it's not, of course, true, right? Because it's not as steep. It's not as
steep. Yeah. The only difference is quantitative. Yeah.
It was only like
but
1 over r, not like 1 over r
But
squared.
also here, it does have quantitative comparison.
Can I go back to you? I forget. Is it backwards?
Sorry. No.
What do you mean? This is.
What?
Yeah.
So here, you were saying this is
What?
it's positive according to Günther, yeah?
Yes.
And according to you it's negative.
Yes. But for omega tau large, maybe it's
And this is something that we have, of course, access to from numerics. And Petri, can we check in the meantime your own calculations? At least from the old calculation of this Pentti Pulkkinen, we found that, first of all, we write it in terms, as Günther does, in terms of sine squared. Because it's the same, except that then there's a -1. And what we find is that this ratio is -1/2. And that means that A1 is still positive.
A1 is positive. You mean...
okay with Günther, right? But not with yours.
No. But in what situation? In a local calculation? Local it may be, but it's not local. Actually, it's another story a little bit. What we've got that A1 or phi1 much larger than phi2 in our theory, is the same for Günther. If we'd like, I'm ready to demonstrate these two functions. Excuse me. Okay, let me, I simply can draw these two functions. Phi1 is function omega tau naught, something in this speed, and this is 6. And phi, no, that's for some stupid reason. And this is phi 2. And so it different, not 2 at the U calculation, but maybe factor 6 or 7. So I'm not sure why in any situation it should be just half. It's a little bit. Well,
And we have access to simulations, we should at least compare.
Okay, maybe we'll compare more detail.
yeah, of course, it is not so. Yes, because it says we find solution on it. Okay, it's interesting. I've got special this one. This is some generalization of Lagrangian polynomials. Guggenbauer polynomial. What is
Guggenbauer is just a Lagrange function, Lagrange function divided by some time.
No. You speak about how to Lagrangian function, not polynomial. It is
Lagrange function, yeah, but when you divide by sign, it will be.
yes, but it is Guggenbauer polynomial. It's another story. Guggenbauer. When alpha equal 1, it means it's some. It is Lagrangian. If alpha equal 1. For example, for operator for differential rotation, alpha equal 3/2. As a result, it will be third, and it will be third again.
But of course, the expansion in terms of Gegenbauer polynomials has always been an optimal one. There shouldn't be any
pay attention
question.
to this equation.
It doesn't expand in the exact solution.
Yeah, and they are not
Angle phi
polynomials.
depends
of
on
course.
third power. Additional sign, because we have got, what is velocity? V multiplied by psi. This is additional sign. Sign in third power. And this is precisely, you can bow for it. And we build a solution analytically. I don't know, maybe I'm pretty sure we're not first. I think Boomba made it or another old person. No, not Boomba, what is his name? From Chile. Dami. I think Dami. Yeah, use it. Right, very, very nice. And pretty, but it's from equation too. Interesting that it's only a function of this equation. Non-trivial. You can find it even in Korn book, in the handbook of. We use this theory, by the way, with orthogonality. No, if you need, I will give you some interesting feature which have very deep physical memory.
All right, thanks. I like the discussion.